Think, Learn, Innovate.
Hi everyone. In today's class, we will find out the steady state error for digital control system. We'll find out whether it will have what will be the steady state error for unit step or unit ramp or for a unit parabolic input for a system given below. So I've drawn the system already, and therefore the forward path function, actually the forward path function, I will write down my GS is given as 1 minus e to the power minus st by s into 1 divided by s plus 1 and s plus 2. As you know, ZOH is represented by this function. Okay, and so as both of them are cascade to each other, that's why I multiplied the both function together. Now we know that actually we have to find out the Z transforms of both the side. So we have to find out the Z transform of both the side. And we know that e to the power st is your Z. So we say that Z equal to e to the power st. So the Z transform of my GS, I can write down directly here 1 minus Z inverse. That comes from here. And then I will find out Z transform of what? Of 1 divided by S plus 1 and S plus 2. So that I can get the function in case of your GZ. Okay. We will apply here partial fraction method. And by applying partial fraction method, I can solve this equation and find out the values using partial fraction method. So I will do a partial fraction method. Partial fraction method. And I will say, okay, 1 is S plus 1, S plus 2 is given by A by S plus B by S plus 1 and plus C by S plus 2. So at first I will find out the value of A. So to find the value of A, what I will do, I multiply both sides by S plus 1 and S plus 3, which is equal to A by S plus BS S plus 1 plus CS S plus 2. Okay, and we know the pole, the value of the pole is 0, so I will say S equal to 0. So if I this S goes away, and if I plug in value 0 here, both this equation will be out, only I will A here, and my A is nothing else but very easy to say 1 by 3. So you know how to do the partial fraction method, but I am doing the method here so that it may be good for you guys to go through the method again. For next case, to find B, find the value of B. What is the pole? S plus 1 equal to 0. So S will be minus 1. So again I will multiply both sides by S plus 1. S plus 1, S plus 3, A, S plus 1 by S plus B, S plus 1, S plus 1 plus C, S plus 1, S plus 2. So this S plus 1, S plus 1 will go away, and I will say S plus 1 and S plus 1 go away. I will say S equal to minus 1, and I will plug the value of S equal to minus 1. If I plug the value S equal to minus 1, this will become 0, and this will also become 0. So these two terms, A and C term, will vanishes out, and so I will get here 1 minus 1 minus 1 plus 3, which is equal to my value b. Okay, so my b is equal to minus half. So I get b equal to minus half. Similarly, to find the value of c, what I will do, I will say, okay, what is the pole? S plus, my god, it's s plus 3, sorry, it's s plus 3, and here also is plus 3. So s plus 1 is plus 3, so s plus 1 is will come, and this is plus 3, so I will plug in the value of s plus 3 here, and s plus 3 equal to 0, so s equal to minus 3. I'll plug this value here. So again, what I will do, I'll multiply both up and numerator with s plus 1, s plus 3, and that s plus 3 and s plus 3 will go away. Here I will say a s plus 3 by s, okay. Then b s plus 3 by s plus 1, okay. And then I get c s plus 3 by s plus 3. So this will go away, and I will write down s equal to minus 3 here, and here s equal to minus 3. So I will plug the values s equal to minus 3, and remember, if I plug the value is minus 3, b and a term will vanish out, and I will only have c term left behind. So if I got c term left behind, so that time I will plug the values of s like this: 1 minus 3 minus 3 plus 1 is equal to c, and my value of c now becomes 1 by 6. So my value of 1 divided by s plus 1 and s plus 3 becomes like this. First term was 1 by 3 into 1 by s. Next term was minus half 1 s plus 1, and third term was plus 1 by 6 into 1 divided by s plus 3. Now if I find out, if I do the inverse Laplace transform of this one, say inverse Laplace, so I will get this equation in the form of, say, t. So what I get, 1 by 3 minus half e to the power minus t plus 1 by 6 e to the power minus 3t. So that's your inverse Laplace transform, and I got this value in form of t, right? So I got this equation in the form of t, and I will now find out the z transform of this equation. So I will take this function, say, name this function x of s, and say I got this function of x of t. So what I will do now, I will find out this function in the z transform of this function. So z transform of any function, say 1, I can write down in this format: n equal to 0 to infinity e to xn and z to the power minus n. So in this case 1, so I get what? N equal to 0 till infinity, and what I get here is 1 into z to the power minus 1 to the power n, and that gives me 1 minus z to the power minus 1. That's your z transform of 1. How I will do this one, only do it as sampling. With the help of sampling, I can find the values of this one together. So how I will do it? I will say, okay, let's sample this one and do the z transform of, say, e to the power minus nt, and I will say t equal to 1. So it will become n equal to 0 to infinity. Xn is e to the power minus n, z e to the power minus n. So this becomes n equal to 0 to infinity. So e to the power minus 1 z to the power minus 1 to the power n and 1 like this. So that's your z transform of this. And similarly, I can find out the z transform of e to the power minus 3nt, and that will give me 1 minus e to the power minus 3 z to the power minus 1. Now, when I got all the z transform of all of them out, I will go to the next page and I will write down those z transforms equation separately. So my g of z, what I got, 1 e to the power z to the power minus 1, right? And this value is for part of ZOH, and next my Z transform of other part will be 1 by 3, 1 minus Z to the power minus 1, then I got plus say 1 by 6, 1 minus Z to the power minus 1, e to the power minus 3, and another part was minus half, and what I got here, 1 minus z to the power minus 1, e to the power minus 1. So my gz, now I can write down z minus 1 by z. Again, z to the power minus 1 will give me 1 by 3z divided by z minus 1 plus 1 by 6z give me z minus e to the power minus 3 minus 1 by 2z divided by z minus e to the power minus 1. Well, if I get this equation, I will do the LCM of this equation. Remember one thing, that this z will go away because I will take all the common of z together and I can get this z out of the equation altogether. And so my gz will be what? Gz will be z minus 1 outside and bracket open. First of all will be 1 by 3. I will do the LCM 1 by 3. Z minus e to the power minus 3. Z minus e to the power minus 1. After that, what I will get? 1 by 6. I will get z minus 1. And I will get z minus e to the power minus 1. And after that, what I get? 1 by 2. Z minus 1. And I get z minus e to the power minus 3. And divided by, I get z minus 1, z minus e to the power minus 3, and z minus e to the power minus 1. So this value and this value goes away, and I have my gz here. Now, you have to find out the error coefficient of all of the above equation. So I have to find out the position error constant, velocity, and your acceleration. So first of all, I will write down all the formula for that. So I got gz for position. The error constant kp is equal to limit z tends to 1 and gz hz, and ess error constant will be 1 plus kp. Very good. In this case, I have to use step input. After that, I get velocity error kv, which is given as limit z tends to 1 minus z inverse by t, gz hz, and I got ess equal to 1 by kv. Note that here in gz, I don't have any value where I can deduct this z minus 1. So velocity error constant here, it will not be applicable. So there will be no velocity error here. And next what I will have is your acceleration error constant. Acceleration error constant, that is Ka, which is equal to limit given as limit z tends to 1 minus z inverse square t square gz hz, and the steady state error is 1 by Ka. In this case also, you see, we will not have any acceleration error constant. So only in this particular problem which we are doing, we are taking here, we will have only one error constant, and that is called position error constant. So I will first find out the position error constant. So what is my Kp? Just few minutes back I have written down Kp is equal to limit z tends to 1, and I have gz hz. My hz is 1. It's already given in the problem. And so I will write down limit z tends to 1. And what I got here, gz 1 by 3. I got z minus e to the power minus 3. Z e to the power minus 1. Then I have plus 1 by 6. Z minus 1. And I got z e to the power minus 1. And after that, lastly, I got half z minus 1. And what I got here? Z e to the power minus 3. And whole this divided by what? Z minus e to the power minus 3. Z e to the power minus 1. Now, if you see it clearly from here, if I plug in the value of z equal to 1, limit z equal to 1, then this term and this term will vanish out. So my Kp, after plugging z equal to 1, what I get? 1 by 3, 1 minus e to the power minus 3, 1 minus e to the power minus 1, divided by 1 minus e to the power minus 3, 1 minus e to the power minus 1. So both of them will go away. And the value which I will get from here is 1 by 3. So what will be my steady state error? It's very easy. The steady state error will be 1 plus Kp, that is 1 plus 1 by 3, and that will give me 3 by 4, and the value is 0.7. Okay. So by this way you can find out the values of your steady state error. I think it's very helpful for you guys. So thank you. If you have any comments, write to me. And one important thing I want to speak once more is that if you go back and if you check this position, velocity, everything, why I have not done your velocity error constant, why I have not done the acceleration error constant, this is clearly seen here that there is a term here 1 minus z to the power minus 1. If I plug in z equal to 1, this term will vanish out. So there will be no error in case of velocity or in case of acceleration. Okay, so thank you. Bye.